Hello, this is Dorian Ramjaton, and this is my submission for the first lab of Physics 2211, Constant Velocity Motion. The overall purpose of this lab is to reinforce understanding of physics principles, such as Newton's second law, the momentum principle, by observing and analyzing the constant speed motion of an object, creating a computational model based on these principles, and comparing the model's predictions with observed positions. I will be using position time graphs to complete this comparison. Before we do so, there are two fundamental formulas we must understand. First, Newton's second law, which states that the force acting on an object is equal to the mass of that object multiplied by its acceleration. More importantly, it explains how forces acting on a system from its surroundings cause changes in momentum over time. Hence, if there is no net force, then the change in momentum is zero, and velocity will remain constant as there is no acceleration. And so ultimately, the computed model should be identical to the observed. The next fundamental formula we must understand is one of the kinematics equations. This one is used to define the final position, in which the velocity, the average velocity, is multiplied by time and added to the initial position, which is pretty straightforward and basically shows how an object at constant velocity travels. With these in mind, I began the experiment. I started by recording a video of a trolley moving in a straight line at constant speed, and then imported it into the tracker software to track the position over time. With this, I was able to create the first position time graph, the observed real-life one. As you can tell, the graph itself is linear, with outliers being due to human error. From this graph, we can identify the velocity, which is the slope of the graph. The graph overall represents the change in position of the trolley within the overall system from when I started the stopwatch to when I stopped it. So the position and time are both initially zero. The final position can be observed on the graph as 0.978 meters, and this occurred at the time of 2.467 seconds. Using the initial conditions, final conditions, fundamental formulas, and the slope from the graph, we are able to create a computational model. Starting on the left side, we input our data into the code, only focusing on the first value of wherever it says vector 0, 0, 0, because we're only concerned about the x-plane. The velocity is the same throughout, so we ensure that the initial velocity is equal to the slope we previously found, 0.3639 meters per second. And we make the final velocity be equal to the initial, because it's constant. Finally, we input our kinetic equation to find the final position, in which the average velocity is multiplied by time and added to the initial position of 0. When we compute it, we get the model and the graphs on the right. Since the position, times, and velocity are accurate, we note that the code worked and we can now compare graphs. Ultimately, the models are very, very similar, except the computed one is much more precise due to it being formulaic and prone to less errors. The real-life one, however, can be impacted by errors, such as mishaps during timing and uneven surfaces, which lead to acceleration by gravity and a non-constant velocity. However, since both lines are fairly linear, I think it is safe to say that the velocities were constant in each model. In conclusion, the graphs were very similar by nature. Even if the axes were flipped and x were negative, the velocity would still remain constant and nothing would change despite the final position. Also, earlier I talked about how the net force was zero in my model. This implies that the push and pull forces cancel each other out. Since we know that air resistance and friction are assumed to be negligible, then we can assume that there are zero forces being added together to give a net zero force. Thank you.